Well, thanks for this introduction. So I would like to discuss different topics related to mainly nuclear superfluidity in neutron stars. But maybe first, I would like to remind that nuclear superfluidity has a very long history, and it was first discussed in the summer of 1957, so even before the publication of the BCS paper. So it was discussed by a bunch of people, so Bohr, Michelson, and Pines. And they discussed the possibility that pairing could explain some properties of atomic nuclei. And here is an example. So if you look at the energy spectra of finite nuclei, you see that there is a gap between nuclei containing even number of nucleons and those with an odd number. And so this was speculated that this could be an indication that this gap is just actually a pairing gap. So there are various other observables that also could be interpreted in terms of pairing. I have no time to go into the details here. But the interesting thing is that they still realized that there is a fundamental difference between BCS superconductors and atomic nuclei, and namely that the nucleus contains a very small number of particles. And so it was not clear to them that if we try to extrapolate these kind of pairing gap values to infinite system, would this gap be the same? So it was still not clear to them, and in one of these papers, and so they were that the present data are insufficient to indicate the limiting value for the gap in a hypothetical infinite large nucleus. And really the pairing mechanism in nuclear matter was the theory for pairing in nuclear matter was actually studied by Bogolubov around the same time. So it was really from the start considering homogeneous nuclear matter. And just 1 year later, this is Arkady Migdal, who predicted that such phase could actually appear in neutron stars. And the first real calculations, studies of nuclear superfluidity in neutron stars were performed by Ginsburg and Kirschnitz. Excuse. So the first studies were performed in '64 by Ginsburg and Kirschnitz in this paper. And one should realize that it was actually even before that neutron stars were discovered. So neutron stars were discovered in 1967. And also it is worth reminding that at those times, several superconductors were known, but the only known superfluid was helium-4. So helium-3 was discovered in '72. So here's so here's the picture of what we think is inside a neutron star. So a neutron star contains distinct layers. The outermost layer is a solid crust, which is made of essentially fully ionized atomic atoms, so bare nuclei with electrons. And as we go deeper inside the star, the nuclei become more and more neutron-rich, and at some point, some neutrons, free neutrons appear, and this delimits the transition between what we call the inner crust and the outer crust. So in the inner crust, we have still an ion lattice with free electrons, but in addition, we have also free neutrons, and these free neutrons are expected to be superfluid. And at about 1 kilometer below the surface of the star, we enter into the homogeneous liquid core, where we expect to have superfluid neutrons, but also superfluid protons. And inside the core of the most massive neutron stars, then we don't really know what kind of particles could be there. Presumably there could be hyperons or other particles. So this still remains very uncertain. No, it doesn't work. So one of the best evidence for nuclear superfluidity, as has been already discussed several times, are pulsar glitches. So pulsars are rotating neutron stars, and pulsars are just spinning not only very rapidly, but also with extremely stable periods. So just to put numbers, if you look for some of the pulsars, the change in the period is about 10 to the minus 21. And if you compare that to the best atomic clocks that one can make on Earth, 10 to the minus 18, so you can see that they are really indeed extremely stable. Still, for some of these pulsars, we observed sudden spin-ups. So here's this famous example. So this is a period as a function of time. And you can see that, well, the period increases because of the loss of electromagnetic radiation energy. And suddenly the period decreases, so the star spin-ups, and then again this long trend of increase of the period continues. So these frequency glitches have been observed in about almost 200 pulsars, and we know about these numbers of such glitches. So the first one was detected in 1969, so very soon actually after the discovery of pulsars. And one of the most remarkable features, apart from these kind of discontinuities, is that the relaxation of these spin-ups occurs sometimes on a time scale of years. Now you can play numbers with typical nuclear constants and numbers, and typical timescales in nuclear physics is more like 10 to the minus 22 seconds. So this was really a clear evidence that such a long timescales cannot be obtained with this usual nuclear physics unless you assume that nuclear matter itself is superfluid. And in this case, the calculations was made in this paper. Then they showed that in this case, indeed, you can have such long timescales. So it was really a kind of clear evidence, confirmation that superfluidity indeed occurs in neutron stars. A few years later, a scenario was proposed for explaining these glitches by Phil Anderson and Ito. And they proposed that glitches are somehow related to the dynamics of superfluid vortices. So these vortices can pinch to the nuclei in the crust. And when they are pinned, then this manifests by a sudden spin-up of the star. And there was some experiments on the superfluid helium carried out in the 80s that kind of confirmed these ideas. And actually, the fact that neutron stars should contain vortices was discussed in this very early paper from Ginsberg and Kirchnitz in 1964. So if we believe that the glitches are somehow related to superfluidity, so essentially what we see is just exchange of angular momentum between the superfluid and the rest of the star, then we can actually try to put constraints on the superfluid reservoir contained in a neutron star. And for instance, we can show that the fraction of the superfluid moment of inertia should be larger than these kind of combinations. And these combinations involves a quantity that can be directly measured from pulsar timing. This is just the spin frequency, the rate of change of the spin frequency, and this is a cumulative glitch amplitude. So all of this can be measured. And if we take, for instance, one of the best-known glitching pulsars, namely Vela, for which 20 glitches have been occurred so far. So we can measure these parameters, and it ends up to something like less than 2%. So the same game can be played with other neutron stars, and we still end up with about 2%. And this 2% represent the fraction of the superfluid reservoir in terms of moment of inertia. So one may wonder, well, if the core of the stars are superfluid, why don't we get much larger numbers? This is actually very small. And the answer was given in the 80s from an effect which was actually discussed in in the context of helium-3, helium-4 mixtures by Andreev and Bashkin, who show that in this kind of mixtures, the two fluids can be mutually entrained by each other in such a way that if we look at the mass current of one species, then it's not just aligned with the corresponding velocity, but it's in general a combination of the two velocities. Now, if you apply this to the core of a neutron star, so we have neutrons and protons. So if we have a neutron vortex here, so we have a circulation around of neutrons, and because of this mutual entrainment effect, the current of neutrons drag or entrain protons around, and the proton currents generate a magnetic field because protons are charged. So this means that neutron vortices actually carry a magnetic flux, and the magnetic flux is directly dependent on these off-diagonal coefficients here. So this sort of entrainment parameters. Now, because of these magnetized neutron vortices, so electrons can scatter off these lines, and this leads to very strong effective mutual friction between the superfluid neutrons and the rest of the star in the core. And so this is also shown in these key papers. And so from this consideration, one expected that only the crust actually could contribute to a glitch. And that's why this was also nicely consistent with only this few percent fractional moment of inertia inferred from glitches. Now, the story is not so simple because also in the crust there are all the phenomena that occur there, and the physics is mainly related to a paper that was written by Anthony Leggett in 1970, who showed that the breaking of translational symmetry in general leads to a depletion of the superfluid reservoir. So a reduction of the neutron superfluid fraction, even if we have at t equal to 0. So if we apply this to neutron stars, so this means that if we are in the crust frame, then the neutron mass current is not just the mass times the neutron density times the neutron velocity, but in general, this quantity, the neutron superfluid velocity, could be lower than the neutron density. And if we are now in an arbitrary frame, or the crust moves with some velocity vc, we also end up with similar kind of combinations of velocities, kind of entrainment as in the core. So the question is how big or how small is this superfluid fraction? And to answer this question, so one has to go into the microscopic physics of this phenomenon. And so one way of calculating this quantity is to apply the Bogolubov-Desjardins equations. In this case, in the nuclear context, it looks like this for the simplest models that are local. So we have a single particle Hamiltonian here. We have the pairing potential here. So in principle, one can have a spin-orbit coupling, but in this context, this is small, so in fact, one can ignore these things. And if, well, in the case of homogeneous matter, this just reduces to the usual, to the BCS theory. Now, we expect the crust to be essentially almost perfect crystal. So if this is the case, then we know that the wave functions should fulfill this plot theorem. And so we have bands with some wave vectors k. Now, this pairing potential actually varies generally very smoothly. So we can then try to approximate this complicated Bogolubov-Desjardins equations, but what is known by the multi-band BCS gap equations. So what we're interested in are these pairing gaps. So here, this quantity is just the pairing strength and just the quasi-particle excitations. And here are some examples of, well, yes, and these equations are well known, of course, in condensed matter. This was discussed already in 1959, but really clear evidence of this multi-band BCS behavior was found in magnesium diboride in 2001. in which case we have two bands, so two different gaps with one critical temperature. And the reason lies in the fact that for these two bands, the pairing interactions are very different. So this translates into different pairing gaps. Now, in the crust of neutron stars, it's a bit more complicated because there are many bands involved in pairing. And the main reason is that nuclear interactions are naturally attractive. So it's easy to pair neutrons. And this shows pairing gaps in different bands. So this is in terms of single particle energy. This is a Fermi level here for one specific density as an example. And so, and this represents the pairing potential. So this is the stick line. As a function of distance from an atomic from a cluster. And this dashed line represents the solution if we just assume that it's a local density approximation. And you see that it's this kind of local density approximation do not properly reproduce the data, and simply because proximity effects are very strong. So coherence length is large. So this means that pairing is a non-local phenomenon. So pairing occurs both in what represent here the liquid, neutron liquid, and also inside atomic nuclei. So, so this is something to keep in mind. Okay, so if we want to calculate the superfluid fraction, so the depletion of the superfluid reservoir in the limit of small currents and small temperature, this is given by this simple analytical formula. So over here are just group velocities, pairing gaps, single particle energies, chemical potentials. And if we further assume that the gaps are small compared to the Fermi energy, the weak coupling approximation, which is generally the case, then the formula becomes even simpler, and it's just essentially averaging the group velocity over the Fermi surface. And if we do the calculations, we find that the superfluid fraction is in some layers of the crust could be as small as about 10%. So there's a very strong depletion.
Excuse me, you assume weak coupling limit, but what is the argument that leads to this argument?
It's quantitative. So I will show if it's in the next.
Because
okay,
I
will show.
Interact with large scattering lengths. You know.
I will show numbers.
Okay.
And yeah, it's a good point. So here's just an example of how the band structure look like. So this is on the left side. And this is just an empty lattice. So this is essentially free neutrons, and these neutrons in the crust. And so you can see that well, this looks very messy, but essentially it's very different from just a free spectrum. And this means that the distortions of the Fermi surface are significant. Here are some examples of the different branches of the Fermi surface. And strong distortion of the Fermi surface means that the depletion, that the breaking of the translational symmetry is very important, and the depletion of the superfluid reservoir is also important. Now, there was other approaches to try to estimate the superfluid depletion. So one of the approaches is to use purely hydrodynamic description. So this is the opposite limit. This is a case of strong coupling limit. And here are the assumptions. So we'll assume, well, usual relation between the superfluid velocity and the phase, and further assumptions of incompressibility of the flow, and also a simplified description of the clusters. So essentially at the end, it's just solving potential and classical potential flow. And the superfluid fraction can be extracted from this flow. And what is found is summarized here. There is a superfluid fraction in different layers of the crust for different densities. And okay, with different scenarios on whether the nuclei are permeable or not to the superfluidity. And here are numbers obtained from band structure calculation. So you can see there is a very strong, very big disagreement between the two. And the reason lies in the fact that this hydrodynamic description is only valid in the limit where pairing is very strong. So the question is, how good is this approximation, weak coupling or versus strong coupling? So there was in 2017 a calculations trying to solve the HFB Bogoliubov-de Gennes equations in a layers where this depletion was expected to be the most important. And so there was still a depletion of the superfluid fraction that was found, but much less than what was obtained with previous calculations. And the differences are highlighted in red. So in these calculations, what they did was to solve just for a 1D lattice, while what was done previously with a 3D lattice. And also there was some approximation on the Hamiltonian, the mean field potentials, just considering simple cosine instead of the full potentials. And there were other approximations that was made. So it was not clear on whether these numbers are reliable or these numbers. So yeah.
What do you get if you do HF with no pairing for the 1D lattice that they did?
Yeah, these haven't done so we don't know. Yeah, and also the way that they calculated the superfluid fraction is different. So essentially, what they did is calculating the total energy as a function of the momenta, and then taking the second derivative numerically. So while in my case, I used this analytical formula that I showed. And they extrapolated also in the same regime of small, vanishingly small currents. So, to better understand the role of pairing, so I repeated the calculations, considering a full 3D lattice, not just a one-dimensional lattice, using the same mean fields, same Hamiltonian as before, and calculating the superfluid fraction with this formula. Now, the pairing gaps are not very well determined. So instead of considering specific values of the gaps, I just consider the range of values of the gaps, essentially from 0 up to the largest values that is obtained in pure neutron matter, which is this solid curve. And we know that this is really a problem. So any realistic calculations, including the role of the surrounding environment and the medium, leads to a reduction of these gaps. But so let's maximize the effects of pairing. And so the results are shown here. So it's a calculations done in one specific layer, considering a BCC lattice. So here's the lattice spacing in Fermis, about 50 Fermis. So we have about 1,550 neutrons per lattice site. So here's the resolution that was used. So it's a 3D lattice, so with 35 points per dimension. It's a spatial resolution about 0.7 Fermis. And so this shows for different values of the pairing gaps. This is a ratio of the gaps with the Fermi energy. So you can see that it is indeed quite small, even for this largest possible gap that is, we know is an upper bound and it's not very realistic. Even in this case, the gaps remain small compared to the Fermi energy. So we are indeed in the weak coupling approximation. And the main feature here that the superfluid fraction is not very much sensitive to the gap. There is some dependence, but it's very small. So and if we go in the case where we neglect pairing from the start, the errors are very small. The deviations are very small. So the deviations compared to the hydrodynamical descriptions is mainly due to this weak coupling regime for which you cannot apply the simple hydro equations. Now, another thing that was concern that was raised is about quantum zero-point motion of these nuclei. So they can fluctuate. And it was suggested that because of these fluctuations, this could somehow increase the superfluid fraction. So here is an example of results obtained taking into account this zero-point motion. So with a simple, just multiplying the Hamiltonian matrix by the Debye-Waller factor using the bare ion mass, and essentially the effect is very small. And this is overestimated because the fluctuations of the nuclei itself is also damped by this depletion of the superfluid. I don't have time to explain in details, but this is an overestimate of the effect. So in all, the conclusion that even if if you allow for fluctuations, if we take into account the strongest possible nuclear pairing gaps, the depletion of the superfluid reservoir remains still very important in these layers, at least. So what does it imply? Well, I've said before that to understand glitches, that the core is strongly coupled onto the rest of the star. Now, the crust itself is, the reservoir is also depleted because of this inhomogeneities. So if we compare two observations, the inferred mass of the Vela pulsar, if we take into account these effects, turns out to be very small. So it's something like 0.7 solar mass. So all this region is excluded. This is a constraint here written in terms of the crustal moment of inertia. So all of this is excluded. This is example of some equations of state. So essentially, we see that the lowest possible mass is 0.7 solar mass. Above this, we just the lines like below this in this region. Now, this is somehow troublesome because we know from supernova simulation that neutron stars at least should have a mass around 1 solar mass, and also from known neutron star masses, we do not expect neutron stars to have such a low mass. So, and at such central densities, the nuclear physics is fairly well constrained by experiments. So it's not like we can tweak the parameters and fit the observations. It's quite constrained by laboratory experiments. So the conclusion is that the superfluid reservoir in the crust is not enough to explain glitches. So we have to go back to the theories and think that, well, what could happen maybe in the core? So we should not forget that in the core we have also protons, and protons can be superfluid. And because they have a charge, they can form a type 2 superconductors with defects, with fluxoids. Now, if there are fluxoids in the core, then this means that these are also trapping traps for vortices. So this can be pinned to this fluxoid. So this can also be a region for storing angular momentum. And this scenario has been studied in some papers, just a few papers. Now, another thing that also could be relevant for glitches, as was already discussed at the onset of quantum turbulence, and it's expected to occur in the layers in the core region essentially below the crust. So not in the full core of the star, but in the region below the crust. So this is something that needs to be better understood. Okay, so now I would like to switch on how one can build actually models of superfluid neutron stars. So we know that neutron stars are very compact objects, so which means that, well, they should ultimately be described by general relativity. And so what we need is some kind of theory that allows us to derive the hydrodynamic equations in a relativistic context for this system. And a formalism, variational formalism, was developed some years ago by Brendan Carter in Paris. And this formalism relies on an action integral in terms of Lagrangian. And the basic ingredients of this approach are the currents. So the time component is just the density, particle number density. And the space components are just density times velocities. So these are the basic ingredients. And so if we consider variations of this action under variations of fluid particle trajectory, then we can obtain the hydrodynamic equations in a systematic way. And these equations look like this. So here are various quantities that appear. So there is this quantity which are just canonical momenta. So the lambda is the Lagrangian, this is a current, so this is a momentum. Another quantity which appears are this vorticity, which is just the antisymmetric derivative of this momentum. So the mathematical term is just exterior derivative, which appears here. This is the first two terms. Well, these terms only is relevant in cases for which particle number is not conserved. Otherwise, just zero. And here are just the forces, external forces acting on each species.
So this is invisible, right?
Sorry?
Invisible hydrodynamic.
Well, depends on what you put in this force. So you can put viscosity, so this can be extended to viscous fluids. And in this case, it's contained in this. So yeah, so the viscosity was also included in this approach. But of course, it's not variational. One has to add the constitutive equations and so on. So this approach was also adapted to the Newtonian context, and the equations take exactly the same form, the same simple form. And the reason is that these equations do not rely on specific definitions of the space-time metric. The key point is that it depends on this kind of derivatives. So in this case of derivatives, it doesn't matter what is the metric. So it just reduces to partial derivative. So this is the reason why the equations look exactly the same, independently of which space-time you like. But of course, the space-time structure is still hidden somewhere, and the underlying space-time structure is contained in, for instance, in the Newtonian context, in some additional symmetry. But I have no time to.
So can I ask a little bit? So
yeah, sure.
Do you mean that the Galilean symmetry is gauged in this?
Yes.
So it becomes a local as a soft symmetry.
No, it's not good. But I mean that the Galilean invariance appears in this framework as a kind of gauge symmetry. Right. So, but the equations looks exactly the same. And this also. Formalisms was extended to allow for elasticity, magnetic field, and combinations of all three. So, especially for the crust. For the crust, we have the solid part, we have superfluid part at the same time, and we can have also magnetic fields. And so the formalism also exists for them. Now, the question that you may raise, well, what should we care about this? We know the equations, and so why it looks like complications to go to the 4 dimensions and this covariance. So what's the purpose of that? So the advantages is that first, well, it's obvious. If we have a covariant non-relativistic approach, it's much easier to compare with the fully covariant relativistic approach. But also, another important aspect is that it's actually much easier to derive conservation laws when you go to 4 dimensions than if you stay in a 3+1 decomposition. And one can use all the tools that have been used in general relativity and to rederive or to derive conservation laws. And I will try to convince you by some simple examples. So one of the famous theorems of classical hydrodynamics is the Kelvin-Helmholtz theorem. And so how it looks in this context. So essentially what this theorem tells us is that vorticity is transported by the fluid, and in this context, it just means that vorticity is Lie transported. So it's a Lie derivative defined this way, and this Lie derivative is 0. So if you transport the velocity with the fluid, then the vorticity doesn't change. It's just what this equation means. Now the derivation is very simple. So we have 2 terms here. So the first one is a double exterior derivative. So it's fully so this means that it's fully antisymmetrized. But this W already contains a derivative. So we have two derivatives, and we antisymmetrized, and this gives just 0. And this one is 0 because of Euler's equation. So Euler's equation is just, well, we assume that particles number is conserved, it is 0. If we have no external forces, so gravity is included here. So this is 0, this is 0, so this combination is just 0. And so you see that.
And what is the velocity that drags the vorticity? So when you take the lead derivative, what is the vector field that actually transposes vorticity?
Well, it's just the fluid flow, the flow velocity. So so in this way, the demonstration is just immediate. There is no calculations to do. And this can be extended to any fluid mixture. It's actually the same argument that the real derivative of the vorticity is transported by the fluid. Now, how about superfluidity? So there's something which has been somewhat overlooked in the traditional literature, where this quantization is introduced in terms of superfluid densities. In fact, the quantization is somewhat straightforward if one remember this old Boson-Lefebvre quantization rule, so where the momentum circulation is quantized. So the true circulation is really in terms of momentum and not superfluidity. So this is quite unfortunate that there's been this somewhat confusion between velocities and momentum, and this was discussed by Carter and Karatnikov in this paper. So how can we account for superfluidity? Well, on small scales, we know that superfluidity is irrotational. So vorticity is 0, momentum is just the gradient of the phase of the condensate. Now, on large scales, if we try to build a hydrodynamic description of range on many vortices, then the vorticity we know is not 0 because we have vortices. And what kind of conditions we can impose? Well, the vorticity is now carried by vortices. So this means that the derivative of this vortex, of this vorticity, is 0 along the flow field of range flow field of the vortices. So one can easily impose this condition. Is somewhat simpler than in its traditional approach. So another thing that can be easily derived in this framework called the Bernouilli theorem. And for that we can use the concept of a killing vector that is well known in general relativity. So what does it mean? A killing vector is just a vector pointing along a direction for which the space-time, or in our case the fluid, is invariant. The simplest case is, let's consider a stationary flow. So what does it mean? It's just that the flow is invariant if it's translated along the time direction. It's just as simple as that. Now, if it is the case, again, the condition is that the lead derivative of any property of the fluid should be 0 along that direction. And this translates into this kind of relation. So we can see now how to extend the Bernouilli theorem. If we have an irrotational flow, then this is 0. And we see that this combination then is constant. Now, another possibility is that if we consider the combinations, these gradients along some flow lines. So this is just, in fact, it's going to be shown that this is this combination. And if there is no force, external force acting on the fluid, then this quantity is just also 0. And here's just an example. If you apply just a stationary flow, then we recover that these combinations, phi is the gravitational potential, chemical potential, then this combination is constant. It's a traditional Bernouilli theorem, but in general, this is this combination. So some component of the momentum that is constant. Now, just an example that has been discussed already several times here, the concept of helicity. So this is the combination of velocity and vorticity. And this measures somehow the degree of knotedness of vortices, taking the words of Moffat. Now, it is quite remarkable that, This is quite remarkable that helicity conservation was demonstrated only a century after Kelvin-Helmholtz theorem. So it took a century to obtain this conserved quantity, and the concept of current in the context of superfluid helium-4 was introduced in 1980. So it is really not obvious in the usual approach to see how this quantity appears. That in the 4D framework is much easier. So the helicity current looks like this. So this is just mean that everything is antisymmetrized. All the indices should be antisymmetrized. Now, if I take the gradient of this, so again, I have two derivatives here that are symmetric, but I should antisymmetrize, so this gives 0. If I have Euler's equation, then this combination is 0, which means that this matrix has some 0 eigenvalue, so the rank is less than 4. But it's also, this is an antisymmetric matrix, so the rank can only be 2. So this means that there's only 2 independent matrix elements. Well, only one matrix element because it is antisymmetric. So if we take the divergence of this current, so we should antisymmetrize back to all indices, but you can convince yourself that it is just actually 0 in this case. So the demonstration is just less than 1 line. And if you try, I did the demonstration using the usual Euler's equations and recombining, and it's not just 1 line. It's much more complicated. But in this way, it is quite straightforward. And one can generalize this concept to superfluid mixtures. And one can show that these combinations, which accounts for the connectedness between different kinds of vortices from fluid X and fluid Y, and these combinations is concerned. Okay, so I will now go to, I skip this, to the conclusions. So the take-home message that superfluidity in neutron stars is actually very well established. It was predicted before the discovery of neutron stars, and one of the best evidence of pulsar glitches and these long relaxation times. However, there are still many things we do not understand about superfluidity in neutron stars, and the main reason is that the main challenge is that it's a multi-scale problem. So we have to go from the Fermi scale to essentially kilometer to the kilometer-size neutron star. It's a multi-component problem, so we have neutrons, protons, leptons, and well, other particles as well could be present. There are also different phases. I don't have time to go into the details, but we expect to have not only isotropic superfluid phases, but also anisotropic superfluid phases. They can be also, well, we have homogeneous phases in the core of the star, but inhomogeneous superfluid phases in the crust. And all of these dynamics, superfluid dynamics, can be coupled to the elastic dynamics of the crust and to the different fluid that are present. Another thing which I don't have time to explain is that we expect also to have very strong magnetic fields, and potentially we can have magnetic field as high as 10^18 Gauss. And something which is also one should not forget about is that general relativity can also matters in this context, and there will be a talk tomorrow to show that indeed this can affect the superfluid dynamics of the star. So there are still many phenomena that we do not understand, but this is also the reason why it is really crucial to have some insight from experiment that can be done on Earth in the laboratory. But also from all the theoretical knowledge that has been acquired from known laboratory support. Thank you for your attention.
Any time for 1 or 2 quick questions? Yes. Just a remark on the strong magnetic field you set 10^18 Gauss, but earlier in the week we learned about 10^12. So does this mean that there is 10^6 uncertainty on the on the magnetic field?
So there is a different range of values for the magnetic field because there are different neutron stars. Yes. So 10^12 is a typical value for it's a normal pulsars. Okay. But magnetic fields, for instance, of 10^15 Gauss have been measured at the surface of some neutron stars, not all, but some neutron stars. And just from stability consideration, simple virial arguments, one can just estimate the strongest possible field that could be present in the core. And it's about
a maximum value.
Yeah, it's a maximum value.
Okay.
So the reasonable values, it's something like 10 to the 16, which is still enormous compared to what we know from laboratory experiments.
Sure.
Can I ask you, when you say about the Kelvin KT, does this mean that this is considered persistent with some kind of Newton-Cartan gravity?
Yes. So all this formalism was is known in the 30s. It was developed by Elie Cartan, and it's just based on this same idea. So gravity also can be included.
Yeah.
So yes, exactly Newton-Cartan.
Given how accurately the pulsar periods are measured, why isn't the time scale for the glitch known better? What limits that?
Well, because the period is known very accurately because you can just measure a very large number of pulses. So you can just accumulate pulses, and you can reduce the statistical errors just by measuring more and more pulses. While glitches, you just once, so it happens once, and then you have to wait for the next one. So it's different measurements.
Sanjay.
So a question that's always bothered me is why don't all neutron stars glitch?
Well, yeah, it's not clear.
The question is, if we have a mechanism that relies entirely on something we expect in every neutron star, what is the underlying cause for the diversity in observations?
Well, the thing is that you need to pin your vortices to store. You need to store angular momentum. So to store angular momentum, well, the way to do that is to pin vortices. So you need to have a pinning force strong enough to do that. And this can depend, we know that it depends on the temperature, right? And the temperature is not the same depending on the neutron star age. So
so you think there could be an explanation for another variable that can help us understand why it could be temperature, it could be...
Yeah, I think so, yeah. But this has to go into the details of the thing on vortex pinning.
If I can just comment a second on this, that you also have to keep in mind that a lot of pulsars are very regularly timed. I mean, they're doing a survey, you look at it, you observe it just long enough to get a timing solution, you move on. So there's a whole bunch of them that may be ugly. I mean, I think for now we know something like 10% maybe that a lot of them might be glitching, you just don't know.
Yeah.
And it's the same for also the time of rise of the glitch, that some of them you don't even see the glitch, you just see that something happened and you build a solution and you infer a glitch. But
Yeah, I just figured that with this Vela one, you know you can watch it and see something at least every few
so
years.
I think the problem there is that you have some pulse profiles and they're not nice, perfect sinusoids. So before you can actually know where you are in phase, you have to, because this pulse profile is doing all kinds of stuff because of various kinds of processes happening in the exterior. So you have to stack a bunch of them before you can time it. And so it's some kind of intrinsic noise of the pulsar that's limiting your accuracy there, I think.
So, okay, let's thank